Hi everyone, welcome. This question, continuous subarray sum, is a medium level difficulty question. It says, given an integer array nums and an integer k, return true if nums has a continuous subarray of size at least 2, whose elements sum up to be a multiple of k, or false otherwise. So a brute force solution give you a double for loop here and a sum operation as well as a modulus operation. Has a time complexity of n cubed, pretty much computationally expensive. How can we improve the efficiency here? The solution actually involves several background understanding. For example, the question subarray sum equals k. If you are not familiar with that, this question can be easily, in my opinion, a hard question. To cover all the bases, let's review all the background knowledge required. It's recommended you also refer to my other video, subarray sum equals k, for some more understanding. One background knowledge required is the prefix sum technique. In brief, the technique says you can use the difference of the two prefix sum to calculate a subarray sum of any subarray slice. You may pause the video to read the information here in some more detail. Now let's review some codes to solve the question subarray sum in general. This function here is to print all the subarray whose sum equals k. It has two possibilities. First, the prefix sum equals k. Second, the prefix sum equal to another prefix sum plus k. You may pause the video to read this information in some detail. The previous version can further be reduced to this version too. In this version, we comment out these two lines when the prefix sum equals k. This is because when prefix sum equals k, prefix sum minus k is 0. So we preload this hash map with a key 0 and value minus 1. This gives us j minus 1. And that corresponds to the zeros index when prefix sum equal to k. With the knowledge how to find all the subarray whose sum equals to k, now we can understand the original problem as the following. So if we break down total prefix sum into two parts, we can have two subarray. The first subarray, we can view it as a remainder subarray with a total prefix sum modulus k, and the second subarray is a multiple of k subarray, and these two parts have a sum equal to the total prefix sum. Directly detecting part 2, the multiple of k subarray, is computationally more expensive. In contrast, detecting the first part, the remainder subarray, with a prefix sum equal to the total prefix sum modulus k, is a lot easier. So we will go with this route instead of directly detecting the multiple k subarray. Now, how do we know whether there exists such a remainder subarray? Well, we can use the idea of a hash map to achieve this goal. Please feel free to pause this video to read the information in some detail. Basically, there are two steps. 1. Find the remainder subarray by using hash map. 2. Make sure the multiple of k subarray has the length at least 2. With all the background knowledge in mind, let's review the question one more time. The original problem is stated here. Now, we know directly solving subarray part 2, the multiple of k, is computationally expensive. Instead, we want to use a prefix sum, including the subarray part 2, to solve the problem. Specifically, we want to break the total prefix sum into two parts. The prefix sum modulus k, the remainder part, and the multiple of k part. So the original problem cannot be translated into this new problem. There exists a remainder subarray part 1 indexed from the zeros whose prefix sum equals to total prefix sum modulus k, including 0. So this remainder can be 0 as well. And the length of subarray part 2 is at least 2. With all the background knowledge introduced, we are now ready to write the code. So first, as a reminder, we want to break down the nums array into 3 parts. First part is the remainder part, or the subarray. The second part is a multiple of k subarray, and the third part is any residual subarray. Okay, to find the multiple of k subarray, I'll go here. We use a two-step. We actually want to find whether the remainder subarray exists using the prefix sum. So first of all, find existence of remainder subarray using prefix sum. And second, if we can find, we want to make sure the multiple k subarray has length at least 2. Ensure multiple k subarray has length at least 2. Okay. So the remainder subarray can also have a length 0. Okay. So now, first of all, we create a hash map to keep track of the remainder subarray, and the key will be the remainder prefix sum, and the value will be the index, what it sum up to the index, the prefix sum, sum up to the index. Okay. And we also want to create a total prefix sum to keep track of the total prefix sum. And now let's iterate through the nums array. At each iteration, we increase the total prefix sum by nums I. And now we also want to create a variable called the remainder prefix sum. This is the total prefix sum modulus k, and this remainder prefix sum will be the key, and there are two conditions that we are sure the multiple k exists and or the remainder subarray exists. Two conditions that remainder subarray exists. Okay, condition 1. The remainder subarray is empty, so means there's no remainder subarray. In this condition, the remainder prefix sum is 0. And the second condition is when the remainder prefix sum, remainder prefix sum is seen before, so now we know it exists. So if remainder prefix sum is in the hash map, then we know it exists. Okay, and so in the first condition, when the remainder subarray is empty, and so we only have this multiple k subarray, what's the length of the multiple k subarray? It will be I actually, or I plus 1, at this 2. So for example, I is 0, length is 1, I is 1, length is 2, so I plus 1, that is 2. And if this condition is met, we know we have at least 2, and we return true. And the other condition is seen before, and so the length of the multiple k is simply I minus the value as looked up by the remainder prefix sum. This gives us the length of the multiple k subarray. And if this is the length greater than 2, we also return true. And finally, we usually will do a hash map here, a learning process equal k if none of the condition map, right? But we don't want to put it here. I want to put it here. The reason is because, well, first of all, the remainder prefix sum repeat itself, and we only want to update it when it's not seen before. Learn it when it's not seen. Also, I increase in the iteration. So if we don't do this, it will be the same remainder prefix sum, but increasing I, and that will give us an error. So I want to keep it here, only learn it when it's not seen before. Okay, so now if none of this is true, then we return false, and that is our code. And now we run it and test it. We submit, and it's evaluating. See how it goes. Accepted, faster than 96% of Python submission. Pretty good, in my opinion. And now we analyze the code for complexity. So it has a time complexity on. Many is because we iterate through the nonce array, so it scales up to n linearly, and the space complexity is also on, mainly because we use a hash map here, and it scales linearly with n. And finally, the code, as you can probably remember from the previous version 1 and version 2, this code can be further reduced to a version 2. So this is utilizing this condition when remainder prefix sum equal to 0. Why don't we preload the hash map with 0? Then we don't need this, right? Because it can be met here, but what it will be the value here. So previously it will be I plus 1 larger than 2 or equal to, so it will be minus 1. So it will be I minus 1, or be the same as I plus 1. So the preload value will be 0 as a key, and index, value is minus 1 as a preload value. Okay, so that's all. Thank you very much for watching. This is a relatively hard question, in my opinion, if you are not familiar with prefix sum and subarray sum equal to k. And hope you find this to be useful, and see you next time.